Hey everyone, in this video we're going to talk about gears in general and specifically conjugate action and fundamentals. And this video is part of a lecture series on mechanical design 2. And so what I want to start with in this lecture and this video specifically is on conjugate action. So if we look at conjugate action, um, one way to do it is to kind of explain what it means and explain what it means as theoretically. But I think it actually helps to first look at an illustration that I have here animated, and I have the link in your notes as well. So to start with, we can see the animation on the right side. So as you can see on the right side, we have two gears that are meshed together and that are seamlessly transitioning together. And if we actually study this a little bit, and I'm going to use the stopped image to kind of analyze what's going on, and you can see the animation on the right side. But essentially what we see is that we have a essentially a line of action that gets created between this point and this point. And as we go along, we see that the gear teeth are touching along that line of action. So there's a line of action where the gear teeth are essentially making contact. And we can see that they're making contact only at one specific point throughout. So that means that the force is distributed in a very easy way, and it's a very good way of designing a gear tooth. Now, obviously, this is an ideal design, and as we can see, there are some problems with this design. If we look specifically in this design, while I erase here, is that this is touching, and a lot of the parts are actually, there's extra parts that are touching. So this is an ideal design, and technically what we would then do is probably cut off this part of the gear so that it doesn't touch on the ends, and we can do some shaping of the gears so that we have a better pattern of contact. But the contact itself is made through what we call conjugate action. And that conjugate action, what it means is that it essentially follows one line of action while there is the gears touching, and it consistently rolls on. The two gears are essentially rolling on each other. Now, the other thing we want to talk about a little bit is just looking at this diagram. We also see that we have a few different lines, and the lines that I'm interested in looking at are these two lines here. So we have this line for one gear set and another line on this side for this gear set. And these lines are essentially the pitch circles. So you can see that the pitch circles are perfectly aligned, and this is what would happen when you have two gear systems intertwined. Now, obviously, as a first step, what we could do is say, let me design a system, and instead of having gears that are this shape, I would design gears that are essentially could be just squares or rectangles. And the problem with that is that you can see that if you put them close together, you're going to have a big problem in terms of what's happening. So by shaping the gears in essentially an involute profile, or what we call doing conjugate action, we actually are able to have this perfect transfer of force between one gear and another. And there's some information in your textbook, more information in your textbook on conjugate action and involute gears and how to build them. But we're going to look a little bit about how to do that and how to process that in this video as well. So let's take out the animation and start with the written part of the video. So let me erase this because it's not very relevant. But essentially, to start with, what I want to do is kind of define what conjugate action means. And conjugate action is what you're seeing in the animation above, or in the video, or in the picture above. So conjugate action is ideal for gear transmission of forces. And essentially, we want to do that geometrically. It makes sense to do that. And so what we can say and how we can describe conjugate action is we can write that tooth profiles are designed to produce a constant angular velocity so they're uh, producing a constant angular velocity ratio during meshing. And what we mean by meshing is when they're in contact together. And so what this really means is that essentially the um, the rotation of both gears is happening in sync, and therefore we have a single point of action at all times. And this is achieved through the involute profile. Now we have another example here below in figure 13.6 where we have a cam and a follower, so different design than a gear, but we have a cam and a follower, and if we were to rotate that cam, we would see that essentially the contact, if we have an involute profile for our cam, what we would have is this contact point would start moving this way, so this would start rotating this way, and essentially we would have this following of the line of action through this cam rotating, and as the contact point rotates on here, we always have this constant line of action. And this is kind of where the tooth profile comes from for gears, and that's how we decided to design tooth profiles. Now, how do we actually construct an involute curve? Well, we can actually do it pretty easily, and in your book there's some step-by-step instructions on how to do it. We're going to do it very quickly just to show you how it's done and how we can do it from a circle with an actual gear on it. It's actually very simple, and we're going to zoom in a little bit, so we're going to exaggerate a little bit the involute curve so that we can see what's happening. But to construct an involute curve, what you would want to do is you would essentially start with a circle. Okay, so just like a gear, we would have a circle. And what we're going to do with this circle is we're going to imagine that we have a string wrapped around it. Okay, so you can actually do this with a piece of string and a circle, or if you have dental floss, you can do it with dental floss too. It actually works really well, and you can do it on a piece of paper. But essentially, let's say we have a piece of string wrapped around, and I'm going to draw the string in green. And what I'm going to do is I'm going to say the string is wrapped around until that green point on the right side. And as I start unwinding the string, what's going to happen is I'm going to start unwinding the string, and I'm going to draw in red. What's going to happen when I unwind the string is, well, I'll do it in green first. So we have, let's say I get to this point, and then I'm going to get to this point, and then this point, and then this point, and then this point. And what we see if we put the points together is we get a shape that looks somewhat like this. And if we now, so let me just fill up the greens so that they're to scale kind of. And now what we can do is we can do it from the other side too. So we could do the same thing and unwrap a string from this side, for example. So let's say it's wound up this way now. Okay, so let's say we have a string that's wound up this way. Then we can unwrap that string as well, and we start getting a curve that looks, oops, sorry about that. We start getting a curve that looks like this. So we start getting a curve that looks something like this. Okay, and little by little, what we're able to do is we're able to construct essentially an involute profile. And the teeth should follow the shape of the involute profile to be able to do the same action that we saw above. And so what we can do is we can essentially say, okay, now that I have this profile right here, I'm going to highlight it in yellow. I can then take it and make my teeth out of this shape. So my teeth are out of this shape, and what I can do then is I can then decide, well, either my tooth, I'm going to draw over it in black. So either my tooth can have a pointy end like this and can be called a full tooth, or what I can do is I can cut it off at the end. So I can cut it at the end like this and say I'm going to have a tooth that's cut off at the top, and that's usually called a stub tooth. So there's two different types of teeth usually, full versus stub. In this case, most of the time we use stub teeth, but sometimes full teeth is a little bit cheaper to manufacture. You don't have to cut off the top. Usually we use stub teeth because it allows us to not have as much interference, which we'll talk about later on. But essentially, this involute curve creation is actually very easy to do, and you can actually do it very simply. In your book, there's more information on it. We're not going to go in detail on how to create involutes. We're just going to assume that all gears are created with this involute curve. And you can also create different angles of line of actions, which we'll talk about later. So the line of action doesn't necessarily always have to be at the same angle, meaning that if I go back to my previous diagram at the top here and erase some of the animations, this line of action, so if we think of like, well, let me just erase everything. So if we think of this as the straight line or the tangent between the two systems, what we can think of is this blue line here that I'm highlighting right now in red is essentially our line of action. And this line of action can have different angles compared to this line. So I'll draw it in green. So we have an angle, for example, of 20 degrees. Okay. Now this angle can be played with, and we can use different angles depending on how aggressive we want the involute to be. Okay, so we can change the angle of the circle to make the teeth smaller or bigger, and more aggressive or less aggressive. But typically, there are different line of action angles that we want, but typically it's usually 20 degrees or 25 degrees, or historically 14.5 as well. Okay, but we'll talk about that a little bit later on as well. Okay, so moving on from this, now that we know how to construct an involute curve, and we don't know all the ways of doing it, but we understand how it works and the fact that it then creates this conjugate action, which is ideal for us. Let's talk about some of the advantages of having this conjugate action and why we actually want it. So one thing that's clear from our animation as well as our cam and follower diagram is that we have what we call ideal meshing. And what that means is we have ideal meshing of the gears together. That's when the gears are contacting together, which means that we then have, because of that, we have less wear and less noise. Okay, so the direct idea of having ideal meshing is that you have less wear and noise, and this is due to the fact that you minimize friction. Now, other things that are very good about this is it's predictable. So as opposed to having a rectangular profile or another type of profile, it is very predictable. And it is very predictable because the force that occurs, so the force transfer between one gear and the other, occurs on the line of action. And it only occurs on the line of action and nowhere else. Okay, so we know there's a single point where the force is happening. Now, in real life, and as we'll see in future chapter, we'll see that in real life there is some distribution of the force, but it is still a point force to some extent. The material might feel the force in different ways, and the stress in the material might be different, but the actual line of action and the force is happening at one point at only once, and it's constantly moving along the tooth as it's moving down, as seen in the animation above. So three other things that are good from this profile is durability. Then it also saves weight. So rather than having full profiles of square teeth put together or rectangular teeth put together, we can actually save weight that way. And because of its simplicity of design and its simplicity in coming up with different designs and different shapes that are always going to be the same, it means that it's easily manufacturable. And it's easily manufacturable because we can create some standard sizes, and we can use these standard sizes, create these standard dies, and then we can just cut always to the same size based on a standard. So we're not going to have infinite number of sizes that we can pick from. We're usually going to have size increments in terms of the teeth that we want, and then we can add those teeth, or we can cut those teeth out of different diameters of gears. Okay, so that's a little bit about the first part of this lecture. The second part of this lecture is we want to go over some of the fundamentals um, associated with gear design before we go into gear trains and a little bit more of the technical aspect of gears and how we're going to calculate sizing of gears and how we calculate the speed transfer, the force transfer, and all these different things. So, um, so as we've said before, when two gears are meshing, and as we've seen at the start of this lecture, when two gears are meshing, their pitch circles roll on one another without slipping. So you can think of two gears meshing together as essentially a perfect system of two um, circles or two cylinders rolling on each other where their pitch circles are. Okay, it's not an ideal way of visualizing, but it actually is happening in that way. There's only a mesh between them so that we can get some force transferred from one side to the other. Okay, if we were just using the friction of the two pitch circles rolling together, we wouldn't get much friction to be able to move one circle from the next. That's why we have these gear teeth to be able to transfer the force. So what we can do is we can simplify the diagram of our um, pitch circles, and we can simplify our diagrams of the gears and start adding some important notation that we're going to have to know throughout the systems ourselves. So let's start with looking at two gears, one pinion and one gear. So pinion is a small diameter gear. A gear is the bigger diameter gear of the two. And let's look at them together and see what we can start analyzing and putting in terms of the different things. So let's start with a line between the two, and this line is going to be the tangent line where the two pitch circles are intersecting. So we're going to have a small gear, okay, and assume that my drawing is perfect and it's actually intersecting right here. Okay, I'm leaving a little bit of a gap just so that we can see. And then I'm going to have a bigger gear. It's going to be drawn next to it, and they're basically in contact together. So just think those two gears are connected together, okay? I'm leaving a little bit of a gap just so we can illustrate some things, but they're essentially touching, the two circles are touching each other. So the next thing we're going to do is, just like we did in our animation diagram, we're going to add a line of action. Okay, and this line of action is going to be at a certain angle to the line that is tangent drawn in black. And so we're going to start calling this angle
phi.
And what we want to do with this pressure angle is we're going to write down, so psi on the side, and we're going to say this is called the pressure angle. And this is the angle where essentially the force is being transmitted. And there's three standard pressure angles that we will work with and 3 that most gear manufacturers work with. So historically, 14.5 degrees was a typical pressure angle that people would work with, but with modernization, 20 degrees and 25 degrees are more and more common. 20 degrees is a standard, 25 degrees is more for high performance gears. And the advantage of 20 and 25 degrees is that you can design some more aggressive designs and get away with stronger teeth with those more aggressive designs. So we're able to design some more stepped up teeth numbers. So for example, if you have 10 teeth on your pinion, you can probably go up to 100 teeth in your gear, whereas in the past with a 14.5 pressure angle, that was not possible due to something called interference, which we'll talk about a little bit later. So the other things that we can label on here, so we'll label this gear 1, this gear 2, okay? Later on, we'll see how we actually use the notation here. It might be a little bit different. The other thing we want to do is we're going to assume that the pinion is driving the gear, so the pinion being on the left side, and it's driving with an angular velocity of omega 1. Okay, so we're going to use omega 1 as our angular velocity, and we're also going to write our radius 1. So radius 1 being from the center to the outside of the pitch circle. And then we can do the same thing here. We can have a radius 2, so sub lowercase r2. Now, in this case, because two gears are meshing together, omega 2 would be going in the counterclockwise direction. So whenever you have two gears put together, especially if it's a spur gear or a helical gear, we have, if one gear is going in one direction, then the other one is going in the other direction in terms of clockwise or counterclockwise. Okay, just by the fact that the movement is, and I'll draw it in green, the movement is down in this direction. So one goes clockwise, one goes counterclockwise based on the down movement. Now, one more thing we can write on here is we can write that we will also have a velocity which is tangential to the two circles. So we can have a velocity on the left side or a velocity on the right side. We can label that velocity wherever we want, okay? Now, one thing that is interesting about this is that if we were, so we're going to define what V is. So V is called the pitch line velocity. So it's basically the tangential velocity of the outside of the gear. Now, one thing that's interesting about this is if we were to have the pitch line velocity and we were to measure it here and, sorry, let me just draw it at the bottom, it'll be easier. So here and here, would these pitch line velocities be the same or not? So try to pause the video here if you want to, but try to think about, would the velocities be the same on the right side than the left side? And would the angular velocities be the same on the left side and the right side? So the answer is the angular velocities are not going to be the same because we have different radiuses. However, the two gears are connected to each other, which means that if they're connected to each other, the tangential velocity has to be the same. Okay, it has to be the same because the velocity where we have this green spot has to be the same for both gears. Okay, the tangential velocity of the outside of the gear has to be the same. Therefore, we can write an equation down kind of defining that. We can say that V, or essentially our pitch line velocity, which is always positive as long as the direction is correct, is equal to omega 1 R1. And we can find the absolute value of this so that we always have the positive. And then we can also say that this is equal to omega 2 R2. Again, absolute value. Now, because we have this, we can then say, okay, we have a definition for the pitch line velocity. So if we ever need to find the pitch line velocity in a problem, we know we can find it through omega 1 R1, or if we have the pitch line velocity, we can find omega 1 if we know the radius, or vice versa. If we know omega 1, we can find the radius. Okay, so that kind of defines our problem a little bit. Now, what we can do is we can take this part of the equation and rearrange it and come up with an equation of angular velocity ratios. So we can say that the angular velocity ratio, so omega 1 over omega 2 by rearranging the equation above, so just taking the omega 2 to the left side, absolute value, would be equal to R2 over R1. So what we're saying is that the angular velocity ratio is a function of just R1 and R2. And since R2 and R1 don't really change, we can say that it's constant between gears. Okay, so let's do a quick example, and let's try and work on a quick example and see what happens if we do a very quick example of what's happening. So, example. Let's say we have a speed reducer. Okay, so we're told we have a speed reducer, and this speed reducer, the start RPM is equal to 1800, and the finish RPM is 1200. Okay, so we need to somehow convert 1800 RPM to 1200 RPM through some sort of gear combination. Okay, so let's draw a first gear. Okay, so we can draw a first gear like this. Okay, this is going to be, so this is typically how we draw the gears. So we have the gear with the teeth here. The gear can be a spur gear or a helical gear. Usually we try and keep it simple. So let's say it's a spur gear for now. Okay, and this gear has an omega 1 of 1800 RPM. Okay, and we'll talk about omega and what it actually means. For now, we're going to keep it in RPM. We could convert 1800 RPM to radians per second. For now, we're going to keep it as RPM because we know that that's the rotational velocity, and we're going to compare rotational velocity. So as long as we keep everything in RPM, we should be good. Okay, so then we're told it's connected to a gear that is supposed to go 1200 RPM at the end. Okay, so now I want you to pause the video and think about whether or not the gear should have a bigger, so if the gear should be the gear or the pinion, or in other words, should gear 2, so let's say this is gear 1, okay, should gear 2 have a bigger diameter or a smaller diameter, okay, in order to reduce the speed. So, all right, so pause it now and think about it. Now, okay, so now let's say you've unpaused or you already know the answer. Then the next gear we would put, I'm going to draw the gear in red, is actually going to have a wider, it's going to have a bigger diameter. Okay, and we'll see the reason why. The reason why is from the equation itself that we just wrote down before with a shaft, and we know that this shaft is going to go at omega 2. So one other thing that we have to make an assumption on is that omega 1 is going to be clockwise. If omega 1 is clockwise, that means that omega 2 is going to be counterclockwise. And omega 2 in this case will be 1200 RPM. So now that we know that, what we can do in order to figure out the radius or the ratio between the two, or the angular velocity ratio, is we can say, let's write down omega 1 over omega 2. And omega 1 over omega 2 as an absolute value is going to be 1800 over 1200, which simplifies to 3 over 2. So that means that 3 over 2 is actually equal to R2 over R1. So if we were to try and find the radiuses, we can then say, well, we can say that the radiuses could be 3 inches and 2 inches, or 6 inches and 4 inches, any multiple of 2 and 3, or any ratio between 3 over 2 that would work, or 1.5 that would work. So in the end, if we were to solve this problem and say, okay, let's just assume that the radiuses are whole numbers and they're pretty small and it'll work this way, we can say that R2 could be equal to 3 inches, and that would mean that R1 is equal to 2 inches. So we're able to find the radiuses of that speed reducer based on the RPM, and we're also able to find that constant omega 1 over omega 2, which would be 1.5 in this case. One more thing that we want to talk about before finishing this lecture is contact ratio. And contact ratio is a concept that we'll have to use to verify that our gear design is correct in the future. But to start with, what we want to do is we want to look at tooth contact and understand how tooth contact begins and happens. Okay, so we can say that tooth contact begins and ends at the intersection of the two addendum circles. With the pressure line. And we will show this through the diagram below, which I'm going to show in a second. So again, the pressure line is also called the line of action. Okay, so we have here a diagram below. So I'll bring it up a little bit so that we have it a little bit closer to our notes. Okay, so if we look at this figure 13.15, we can see that we essentially have one of the gears drawn. So let's say we have this gear circle that's at the bottom here, okay, going like this. We then have our pitch circle, which is kind of the middle of the gear. And then we have our addendum circle as well, shown for us with the gear tooth basically looking something like this. Okay, so we have our addendum circle, and then coinciding with that, we have another addendum circle that is, so I'm going to erase that bottom line just so we have it clear. We have another addendum circle for the other gear that's shown here. So that would be a gear that's intersecting with the other one. And what we can say is the pressure line or the line of action goes across this way. Okay, so we have the line of action going across this way. And as we approach a line of action, the contact between the two gear teeth is going to happen here, and it's going to happen throughout between. The two teeth are going to be rolling against each other, and it's going to end right here where the addendum circles essentially stop meeting. Okay, so the idea is one addendum circle meets with a tooth, you start a contact, and then you go until the other addendum circle ends by touching the tooth. So we have this pressure line that happens between those two things. Now, the interesting thing with this, and I can show you this as well on the animation at the top, so let me go to the top really quick and show you on the animation. We have the exact same thing here, where we have essentially, right now, a tooth is in contact here. as we move along, and let me show you on the actual animation. So if I bring up the actual animation, it might be easier to see. So if we have the actual animation here, let me make it a little bit smaller. So we can see that we essentially have the start of contact happens once the tooth goes to the addendum, and we can see that at the very end, once the addendum stops touching, we release and we start again from the back. Okay, so very similar concept in terms of what's happening. Now, going back to our notes, we can then start writing some equations based on this arc of action or this this type of system analysis. So we're going to write a few equations down and then kind of come up with an idea as to how we're going to use this and how we need to think about this problem. Now, the one thing that's interesting is that we don't always have to have only one tooth connecting at a time. So we can actually have multiple teeth in contact at a time, because we can have one tooth being within the process, within 75% of the process of rolling off the other tooth. And we could have already the next tooth engaged with the next one. So that means that we would have two teeth in contact at the same time. Not two teeth the whole time, but essentially once the first tooth gets out of contact, the other one would already be in contact. Okay, so let's talk about it a little bit. So the arc of action, which is going to be called A to B, okay? So the arc of action is along AB going through the pitch circle. And we can say that this arc of action, and we're going to call this Q sub T, which is Q total, is going to be equal to QA plus QR, as seen on the diagram. You have a QA and a QR, so it's arc of approach plus arc of recess. Okay, and we can define this arc of action, and we can say that this arc of action is actually equal to lowercase p. And this is the lowercase p is the circular pitch. Okay, so it's a distance from one tooth to the next. Then we can also write a term called M sub c. And you have to be careful with this term M sub c, because you don't want to confuse it with M being module. Okay, so it's M sub c is going to be equal to contact ratio. And what the contact ratio is essentially we can play around with our distance of QT, and we can make QT either greater than our circular pitch or smaller than our circular pitch. Now, you can't really make it smaller than your circular pitch. You have to make it bigger. But if QT is greater than your circular pitch, what we get is that essentially if MC is equal to 1, we have a one tooth in contact at a time. But if MC is greater than 1, which means that QT is greater than the circular pitch, we have more than 1 in contact. And typically, we want our MC, we want to verify that our MC is equal to 1.2 or above. So we actually do not like to have only one tooth in contact at a time. We actually prefer having two teeth in contact at the same time, because two teeth in contact means it's safer. It means that we have a safer system with a safer contact ratio, so that two teeth are taking the load as opposed to just one tooth taking the load. Okay, so this concludes this lecture on general gears and on fundamentals.
In the next lecture, we're going to talk about interference as well as gear trains. So we'll see you in the next lecture for that.